Hello, everyone. So I'm happy today to present to you HACL, which is a new verified modern cryptographic library. And this is joint work with Kartik Bhargavan at INRIA and Benjamin Verdush also at INRIA and Jonathan Plotsenko, who's at Microsoft Research. So it will not come as a surprise that crypto code is vulnerable, even if it appears in somewhere in the comments that something doesn't happen, because well, sometimes it does, and humans are not perfect. So OpenSSL has shown to have a bunch of problems for memory safety, side channel, and even arithmetic just over the past year. And unfortunately, this is not just OpenSSL, which is a big and old library. Salt, which is much more modern and recent, also has had some flaws. And like the NSS library, which is Mozilla's library, and so on and so forth. So the issue here is actually well known even of practitioners. And this is a slide from Emilia Casper from Google, and who's also part of the OpenSSL core team, where at Real World Crypto 2015, she actually highlighted the need that crypto practitioners, like the crypto developers have for formal verification in order to improve the trust that they have in their code. So how do people go about that? Well, you can actually aim at verifying different parts of the software. So some projects aim directly at verifying assembly code. This is the case of Veil, which was presented earlier this year, and also Jasmine, which is the talk that's coming next. And the advantage of assembly is that because it's so low level, you have the most control. So you can get good side channel guarantees. This is obviously the fastest code, and you don't rely on any compilers, so you don't have to trust those compilers. The cons is that, well, because it is so specific and low level, it's actually difficult, and there's a lot of work to put in. You could question the scalability of those approaches. Then you have C code, which is a bit higher level. And for instance, you have the verified software toolchain that tackles C code. And there's also, coming session, a talk about that here. And the advantage of the C code is that it is portable. And I mean, pretty much any cryptographic primitive has a C implementation as the reference implementation that will be distributed everywhere. It also provides decent speed, but then you start to, you need to trust the compiler. And well, no one really knows what the compilers might introduce, in particular in terms of side channels. And the last solution you can go with is using high-level languages for those proofs. And the idea here is that those languages will be designed to actually build easier proofs. So it's easier to build larger projects with those, but then it's slow. You have usually a large trusted computing base, and you get almost no side channel guarantees. So from those, what do we propose? Well, actually, we still suggest that you should go for a high-level language. And why do we think so? We think so because we want to get rid of legacy code. The aim of this library is to be complete and standalone. And so we wanted to re-implement all the algorithms, and we needed a method that would scale reasonably well, and we wouldn't spend years on that. So to do so, we chose FStar for scalability. But because of the drawbacks of high-level languages, we also decided that we wanted to distribute C code with the idea of providing, so it would not be the fastest code out there, but at least it would be reference code that everyone could trust and that would be easy to distribute and also to review, because like very few people are actually willing to read FStar and understand it, while C code is very well known. So quick word about FStar for those or the many of you who don't know it. This is a functional language, which means that it is a la OCaml, but also it has a richer type system, which allows for advanced verification. So in that sense, it could be considered a bit more like COG. And the key difference with COG is that you have some proof automation, because we have an SMT backend that basically lets the proof system discharge some verification conditions to Z3 in our case. And we have different backends for the F-star language. The original ones were OCaml and F#, but now there's also a C backend for a subset of the language. And this is the backend that we'll use for the library in order to get our C code. So the C backend is relatively new. It was presented earlier this year at ICFP. And the idea is that there's a subset of the F-star language, which we call LowStore, which can be considered basically as C code written in F-star. And there's a pencil and paper proof in that paper that you can actually safely compile that subset of the F-star language to C code. What does it mean? Well, basically, you have, we model a C-like memory model with a heap and a stack and a pushing and popping frames mechanism. We only allow restricted types in F-star, so you can only use buffers and immutable structs and machine integers. The code has to be first order. There's no high order for that subset, except for some combinators that we use for loops. And we also exclude the hard-to-prove C features. So in particular, no address taking and no integers to pointers casts. The crucial idea here is that although this might seem a bit restrictive, this is actually enough to implement crypto in LowStore or in C. And if you survey the existing reference C code, it actually fits into that subset. So it's constraining when you write the code that will actually get compiled to C, but for all the proofs, you're not limited. The proofs will actually go away during the compilation process. So for the proof part, you still benefit from the whole language, which leads to the motto of LowStore, which is basically the code is low level, but the verification is not. You still benefit from the whole language. So what happens during that compilation process? Well, you start by verifying your code, and if the compiler says yes, then there's a series of formal translations where first all that is ghost or proof gets erased, and then we leverage on a new tool called Kremlin, which will take the LowStore code and convert it into C-Lite. So C-Lite is a subset of C, and interestingly, C-Lite is the input language of the CompCert verified C compiler, which means that once we get C-Lite code, if we wish to compile it with CompCert, we can actually get verified code all the way down to the binary. Of course, you can also use GCC or Clang, and that's going to give you better performance. Also, note that we made a huge effort on the readability of the outputted code. And there is a proof of trace preservation, which means that some of the secret independence guarantees that we have in the F-star source code are also propagated to the C code. So this is an image of the library, and I want to quickly explain what a verification workflow is before going into a bit more detail. So the idea is that on one side, we inspire ourselves from the state-of-the-art code that exists at the moment for the primitives that we implemented, and we port it to LowStore code. So that's the first step. Then the second step is that we actually read the standards, so be it an RFC or a NIST standard, and we take that standard into pure F-star code, like the shortest possible implementation we can make, and the easier to read, basically. And then we perform 3 independent verification tasks. We want to prove memory safety, and that leverages on this LowStore subset that we talked about. We want to show secret independence. Basically, secret independence is showing that if you take different execution traces of the program, they are indistinguishable from the secret. And functional correctness is basically showing that the LowStore code and the pure F-star specification are matching on all input and outputs. So basically, once we have all of that, then you go through a first pass of F-star verification. If it says yes, then you go to the Kremlin compilation pass, and if everything goes through, you have your verified C code. If it does not, then you just go back to your code and keep tweaking the LowStore code to make it fit within the constraints. So to give you a shallow idea of how memory safety works, this is a top-level declaration of a LowStore function. And the idea is that the code is stateful. So what you see here is that you have a contract with a pre and a post condition that need to be verified. And then you have the argument with their types. And so one of the F-star specificities is that you can add refinements to the types. So for instance, Mac here is a buffer of bytes. You can trust me that this is a buffer of bytes. And we specify that its length has to be 16. Then the pre and post conditions are actually indexed by those H, H0, and H1 values, which correspond to the memory state of the program. And so basically, the function is constrained by some predicates that have to be verified on the arguments and that have to be verified by the memory when you call the function. And then, if that's OK, you get some new properties about the memory state of the program when the function returns. And why this is interesting for memory safety is that we actually specify that we want all the pointers, all the buffers we use to be pointing typically to valid memory location with the appropriate length. And this is what is going to guarantee that we cannot read out of bounds and so on and so forth. Similarly, we have this stack effect on the left. And without diving too much into the details, for instance, this tells us that this function is not allocating or freeing anything, which again, we can leverage on to build proofs. Now, secret independence, as I said, is basically, so secret independence is something that all the reference crypto code in C abides by. But what we do is that we use a more principled manner of implementing it in F-star. And the idea here is that we distinguish between secret integers and public integers. And the secret integers are abstract, so they are seen as completely different than the public integers by the F-star type system, so that basically you cannot branch on them, or you cannot read, you cannot take them as an index. And so to prevent branching, typically what happens is that the only way you have from the secret integers to retrieve concrete values is to go through this function v, which is annotated as a gtot function. That basically means that the result of the function is ghost, so the type system imposes that if the result of that function appears somewhere, it's going to be erased, and so you won't be able to get it in your concrete code. Similarly, we restrict the interface on the secret integers, so you don't have equality operators or operators like the division, which are known to be non-constant time on some platforms. So we can actually restrict what's allowed and what's not. And that's how we make sure that the resulting traces will not depend on the values of those integers. And the last bit is functional correctness. So functional correctness, as I said, is about mapping your low-level code to a higher-level spec, both written in F-star. So taking the example of Poly 1305, this is a message authenticating code algorithm, and it has an underlying field, an underlying prime field that basically you need to re-implement because you want the operations to be both constant time and the fastest possible. And so the idea here is that we want to separate like the low-level implementation of that big name library from the high-level definition of it and map the two. So this is actually the full Poly 1305 specification in F-star. So as you can see, it's not that much longer than the RFC pseudocode, especially since there's a bunch of text that goes with that pseudocode in the RFC. And what we claim for that specification is that it's short, and it's easy to review. Even if you don't know F-star, this is actually a very small subset of the language which looks very much like Coq or a camel, and which you should be easily enough able to read. We use arbitrary precision numbers here, so there's no need to know much about like the way the bignum is implemented. And interestingly, you can compile it to a camel using bignum libraries, so we can actually, even after reviewing that code, we can still compile it to executable code and test it thoroughly. So we have good trust in the fact that this code is actually correct. Then the second part is that you actually need to implement the real thing. So this abides by the kind of optimization that the C code, the reference C code is doing. We use the secret independence I talked about, and obviously, like the actual code is about 5,000 lines long, so it's much longer than the specification. But at the end of the day, what you get from it is the last line, where you actually say that in that MAC buffer, in H1, which is your resulting heap, the value that you get is equal to the specification poly1305 function applied to the original value of your input and the original value of the key. And this is entirely proven by the F-star type system, so you know that they have exactly the same input-output behavior. So that's the idea for functional correctness. Now, one of the advantage of a language like F-star is that because it is meant for proofs, it's very expressive and powerful. And using the same kind of idea we did for the secret integers, we can actually give an interface to what we think vectors are. So for instance, like in the top right corner, this is our interface for a couple functions on a vector of 4 UN32s. And like underneath is actually a C wrapper for the corresponding functions with intrinsics. And the idea is that we specify what we think vectors are, then like this is used to write a specification, like HACL-level specification. Then we will write the corresponding LowStore code for it. It can be run using the actual C wrapper that I showed. And then you just need to show that the specification that you initially wrote from the RFC matches the vectorized specification that relies on the interface you wrote for the vectors. And if you trust that your interface for the vectors is right, and this is what you need to review, then you end up with a correct, verified, vectorized version of a cipher. And in the case of ChaCha20, which was actually designed to be easy to vectorize, we actually get competitive performance with assembly code using that mechanism. So a couple figures. So these are HACL store lines of code and verification time. So as you can see, the total number of lines for the actual specification is relatively low. I think 800 lines of code is something reasonable for people to review, especially since all of that code can be run and tested, unit tested. Then, well, obviously code and proofs is a bit longer. Then, well, the numbers of lines for the proofs is a bit arbitrary because you, like F-star is partly automated, so there's a balance between putting more automation, but then you have less lines of code, but it takes longer to verify, or increasing the amount of annotations, and then the verification time is faster. A side note on the verification time, which I think are still reasonable, is that memory safety, surprisingly, is actually costly. So we've worked a lot lately to reduce the verification times, and we can actually drop, for instance, for SHA-512, the verification time to about 10 seconds. So this is coming down, and we aim at having something where functional correctness is the hard part, and memory safety would be almost for free. Now, the chart is a bit small, but basically what you need to take away from those supercore benchmarks is that compared to the supercore preference implementation, we are systematically faster. The only caveat is ED25519, which is a signing algorithm, because we're not relying on pre-computation. So we're actually faster than the original reference C implementation in supercop, and not the Ref10 implementation. But that one aside, we are actually as fast, if not faster, than all the non-vectorized C implementation for the rest of our primitives. And we're still obviously about 30% slower than assembly code, but this is inherent to the nature of C code. Another interesting thing is that we made a lot of effort to port that code into the real world, and so we're very happy to say that Curve 25519, like the version of HACL store, is going to be shipped within Firefox 47, because it has been included in Mozilla's library, crypto library, NSS. It's about 20% faster than the previous version they had. And I think this is our first lesson, which is that they actually accepted to take our code because this code is verified, and they were able to include the verification and extraction mechanism to their own CI. And so we claim that verified code can help with performance because like people are more willing to take it than those newish implementations, which no one is really sure are totally bugless. Also, it was a very good thing for us to go through the actual Mozilla's code reviews because it helped a lot to produce better looking C code. And we also argue that this is one of the big advantages of C, is that you can review the generated code, while if we generated assembly, it would be harder to do so. A second project that we've been contributing to is the Everest project. Everest is about verifying the HTTPS stack, and well, like the bottom of that stack is actually the crypto provider. So now we have a verified crypto provider for the Everest project with HACL, and it's not just about C in this particular case. So a lot of the code in the Everest project is written in F-star, and when you use HACL from its F-star APIs, you actually have much more detailed information which you can leverage on either to write protocol proofs or cryptographic proofs. And an instance of that is a paper that was presented at Auckland this year on implementing and verifying the TLS 1.3 record layer, which uses the actual HACL primitives. And lastly, the Veil assembly language also has a specification in F-star, which means that for the primitives for which Veil would be faster than HACL code, for instance, we can actually share common specifications so that HACL and Veil can be interacting. So of course, there's still a bunch of work going on. I think the main limitation of our methodology is that we have a large trusted computing base. There's a large trusted computing base around F-star. There's also a large trusted computing base around the SMT solver. And these are not going to go away immediately, but we are working towards making things better. And also the Kremlin tool just has a pencil and paper proof for now, so it would be amazing if we could actually verify the compiler itself. We also want to have better automation, and this is, I think, generally true for formal methods, and less redundancy. So nowadays, we have that specification code and that low-level code, and in some cases, we would love to actually merge the two to have only one implementation and automate that process. And we're working on a new backend of WebAssembly plus JavaScript so that it's going to be easy to distribute into browsers as well. And well, to conclude on the library side, we're still working on including more primitives. We initially started with the salt primitives because that was a nice small but self-contained set. Now we also want to include other primitives such as P256 or RSA PSS. And of course, we are going to keep pushing more primitives into Mozilla. So hopefully you'll see more of those shortly. Thank you.
We have some questions. Hi, Yuding from Baidu. I noticed that your library has been merged to the Mozilla CI, right?
Yes. So
I heard about that Mozilla has two teams. One use F-star and another use Rust. And do you think your project has the competitive speed of the same implementation in Rust?
So I don't think Rust and F-star are really competitors because I think they actually do different things. So Rust typically is all about memory safety.
Yeah.
And I think the advantage of F-star is that we actually get functional correctness out of the code. And in that sense, I think Mozilla should keep pushing on the work they're doing for Rust. But for instance, this LowStore code, like if we could have something that looks more like a Rust front end for that particular subset of F-star, and in a sense, if we were able to let people code in Rust, like they could get the memory safety for free in some sense, and then if we could use the F-star framework to actually prove the rest of the properties we have around it, I think that would be a very interesting idea. We're far from it, but like that's how I see the two going on, because F-star can do things that Rust cannot, and Rust, has all automated, and this is obviously not something we have and we can have shortly in F-star.
Thank you.
Boya from Academia Sinica. Thanks for the talk. And I have two questions about LowStore. So is the compiler verified or not? And to C, LowStore to C. And the other one is, there are actually several languages for like formal verification for C like code, pharmacy, and also there's definitely. So can you compare the features between LowStore and these languages? So why do I choose LowStore instead of Daphne or Pharmacy?
Right. So for the first question, which was about the compilation from LowStore to C, right? So there's a pencil and paper proof that that translation is semantically correct and also preserves traces. So all the properties that we get on the LowStore code, which is, well, it's F-star, basically. We still get them in the compiled C code. So the methodology is verified on paper, but the tool itself is not verified. Like the tool is just a compiler that implements a verified method, but the tool itself is not verified. So my claim is that by using F-star and thus LowStore, we can integrate into that bigger framework, in particular with the Everest project. So we can we can be reused for crypto proofs, we can be reused for protocol proofs, and we can interact with something like Veil, which will have some precise specification. I don't think this is something that is so easy to do if we use, for instance, Pharmacy. Because Pharmacy is immediately targeting. So to me, the advantage of Pharmacy is that you take existing C code and then you prove it, and you don't have to touch the C code. In LowStore, you have to re-implement everything. But if you want to actually build a new project, then I think using F-star and LowStore is more powerful because it scales better, basically, and it's more expressive than Pharmacy. And for Daphne, Daphne is just a different approach because it's more. Daphne is an imperative-like verification language, while F-star is a functional verification language. And I think this is more a matter of preferences. I like to do proofs in a functional verification language. But it's very
Thank you.
Hi, Vince from Alibaba. Great work. And I'm just curious to know that how many people and months does it take to build and verify such library?
Well, so there has been many iterations. It's actually difficult to answer precisely. What I would say is that if you want to implement symmetric cipher, for instance, I think it would be a couple days, less than a week, if you're working with someone that knows the language and the verification tools. So that's pretty easy. Now, if you want to verify something that has a big num library in it, then I would say it's maybe a month. And it depends on the complexity of the implemented, like the actual primitive, obviously. But for something like a new curve, I think at least a month would be necessary, and then it could be going beyond that if it's a new curve, which we haven't done yet, with a different structure for the field, for instance.
Okay, thank you.
Thank you.
Hi, Samuel Gritter from MIT. I was a bit surprised about your table where you showed different approaches, and you had the verified software toolchain approach, and it's the untrusted compiler. So I think you are referring, it uses CompCert, so I think you were referring to side channel freedom, and that this is not preserved by CompCert, I guess.
Right, so I'm sorry, I didn't.
Yeah.
So, okay, the untrusted compiler was more about C. What I meant by that is that, like most C compilers that are used for production are actually untrusted, and indeed, like we do use CompCert actually if we want to produce to generate C code. Unfortunately, CompCert is not yet on par with Clang or GCC for performance. So we want the C code to still be somewhat competitive with assembly, then we kind of have to give up on the verified compiler part. But I agree that we can indeed get C code fully verified using Concert, and I'm sorry I didn't make that clear enough.
And with respect to this side channel freedom, I found that your approach of secret integers in the type system very appealing. But is it already, or do you have plans to give a story of how the compiler would preserve these guarantees that you have in the types?
No, so for now, what we claim is that we have secret independence in the C code, the resulting C code, but there is no guarantee about whatever is preserved going down to the binary.
Okay, so the proof from LowStore to C, you proved this already
yes,
in paper?
So the trace preservation holds from LowStore to C, but under C we don't have any claims.
Nice, thank you.
Great talk. So let's thank the speaker again.
Thank you.